Next, we are going to study section 77. The title is Residue at Infinity. We are going to learn a theorem which is quite useful. What I mean is that sometimes it is more efficient to use than Cauchy's residue theorem that we have just learned in the previous section because it involves only one residue to evaluate integral. You can see this theorem and also in your textbook. To see this, okay, let's check it some prerequisite analogy. We suppose that a function f is analytic throughout the finite plane except for a finite number of singular points interior to positively oriented simply closed contour, this contour here in the figure. Then we assume that there are several finite several singular points here. Then we consider a circle which contain this contour C. First, let R1 denote a positive number. This is R1, which is large enough, that to contain this contour C, so that C lies inside the circle, defined by absolute value of G is equal to R1. You can see this figure here. Then we know that the function f is evidently clearly analytic throughout the domain given by this absolute value of G is greater than R1 and less than infinity, and we know at the end of section 74 we considered a point. It's called the point at infinity, which is an isolated singular point of f. Okay, we revisit that part here. We have defined another additional isolated singular point, the point at infinity here. We at the time we look at it by visualizing with the Riemann sphere here with this figure. There is a one-to-one correspondence between the point on the sphere and the point on the complex plane. We say that extended complex plane, which consists of the normal complex plane and the point at infinity, we denote this point at infinity by this notation. And then we also consider as reason given by this absolute value of G is greater than R1 and less than infinity. With this reason, f is analytic. We said f is f has an isolated singular point at G naught, which is equal to infinity. What I mean is the point at infinity. this definition is quite well defined. Yeah, makes sense. Because when, okay, in the section 24, we have a definition of singular point of a given function f. In this definition, if a given function f fails to be analytic at g0, but is analytic at some point in every neighborhood of g0, then we say f has a singular point. In our case, with the point at infinity, when g0 is replaced by infinity, this statement holds. Yeah, f fails to be analytic at infinity, the point at infinity. Yeah, because the point at infinity, we can, with the point at the point at infinity, we cannot evaluate any function f. So this is naturally hold. But it's analytic at some point in every neighborhood of g0, which is equal to infinity. Yeah. Even we cannot evaluate at any value of f, but there is a point, such that f is analytic, in every neighborhood of g0. For example, we can take this region. Then in this case, whatever we choose within this region, we can make this statement hold. Okay. Also, we can check it. The second condition, isolated. A singular point g0 is said to be isolated if the following condition holds. The condition is there is a deleted epsilon neighborhood given by this. Absolute value of g negative g0 is greater than 0 and less than epsilon, throughout which f is analytic. In this region, f is analytic. In our case, so we consider this region, then the point at infinity is not included in this region because we exclude by definition inequality. So which means that this region is a deleted epsilon neighborhood. Okay, do not contain infinity. So the point at infinity actually satisfy with the definition, the conditions of definition. So it is quite well defined. However, with the point at infinity, we look at a useful theorem here. The theorem says if a function f is analytic everywhere in the finite plane except for a finite number of singular points interior to positively oriented simple closed contour C, then we have this. The integral along to contour C, f of g dg, is equal to 2 pi I times residue g is equal to 0 of 1 over g squared times f of 1 over g. This is quite nice result because this result only involves only a single residue here. Okay, let's prove it.